Alright, hello everyone. Welcome back to Discrete Mathematics and its applications with me Adila Krishnadi, and this time we are going to talk about operations on relation. So let's get started. So operations on relation uh, are things you do to get another relation. Notice the difference between these and properties of relation that we discussed in the previous video series. In this video series, we will talk about operations on relation, which include all set operations on relation, and then inverse operation, and then composition, as well as powers of relation. So the first one is set operations over relation. Note that since every relation is a set of tuples, as we define in the one of the earlier videos, then all set operations are applicable to it. So let me repeat. So because it's a set, then all set operations are applicable. So for example, if you have binary relations R1 and R2, then the union of R1 and R2 here is a pair of A comma B, such that either A comma B is in R1 or A comma B is in R2 or both. Similarly, intersection is simply just intersection of R1 and R2 is simply just a set of pairs A comma B, where A comma B is in R1 and A comma B is in R2. So the intersection of R1 and R2 contains all pairs that appear in both R1 and R2. Now the difference operation is defined as in the usual, usually as in sets. So R1 minus R2 is simply set of pairs A comma B, such that A comma B is in R1, but this pair A comma B is not in R2. So you take all pairs from R1 and then take out the pairs that are in R2. Now the symmetric difference, like in symmetric difference of sets, symmetric difference of two relations R1 and R2 is the union of R1 and R2 minus the intersection of R1 and R2. So in other words, the symmetric difference of R1 and R2 contains all pairs A comma B, such that either A comma B is in R1 or A comma B is in R2, but not both. So that's the difference. You see the difference between symmetric difference and union. And finally, the complement operation is defined as such. If you have a relation R, and then the complement of R, which is denoted by R with an over line here, it is defined as set of pairs from the Cartesian product A times B that is not in R. So A comma B is in the complement of R if and only if A comma B not in R. So of course you see this definition as defined for binary relations. However, this also holds or applies to any n-ary relations, provided that both R1 and R2 have the same arity, and the Cartesian product in the complement is over n sets where R is defined. Now let's have an example here. So suppose you have set A containing the numbers 1, 2, and 3, and then B containing the integers 1, 2, 3, and 4, and you have two binary relations defined on A times B, where R1 contains the pairs 1, 1, 2, 2, and 3, 3, while R2 contains the pairs 1, 1, 1, 2, 1, 3, and 1, 4. Now let's compute R1 union R2, R1 intersection with R2, R1 minus R2, R2 minus R1, and then the symmetric difference between R1 and R2, and the complement of R2. So let's start with R1 union R2. Here is R1 union R2. So you take all pairs from R1, 1, 1, 2, 2, 3, 3. And then you add the pairs from R2, of course excluding the duplicate. So you essentially add 1, 2, because 1, 1 is already there, and then 1, 3, and then 1, 4. So this is R1 union R2. Whereas R1 intersected with R2 is the set of pairs such that these pairs are both in R1 and R2. So if you see R1, in R1 you have 1, 1, 2, 2, and 3, 3. Whereas in R2 you have 1, 1, 1, 2, 1, 3, and 1, 4. Now looking at these two sets, the only pair that appears in both R1 and R2 is 1, 1. So you see that 1, 1 is in R1 intersected with R2. And this is the only pair, so this intersection contains only just one pair. Now R1 minus R2 is obtained by starting from the pairs in R1 and then you take out from these pairs the ones that are in R2. Well, the good thing here is that you see the only pair here from these three pairs, the only pair that is also in R2 is 1, 1. So you cross out 1, 1. Therefore, you get R1 minus R2 contains the pair 2, 2 and 3, 3. Now, similarly for R2 minus R1, you take the pairs in R2 but not in R1. So that is 1, 2, 1, 3, and 1, 4. Now, the symmetric difference of R1 and R2, as in the definition, is the union of R1 and R2 minus the intersection of R1 and R2. Now, if you see there, that means you have the union, which is here. Let me list the pairs here. Minus this, which gives you, of course, well, 2, 2, 3, 3, 1, 2, 1, 3, and 1, 4. Right. And finally, the complement of R2 is, well, A times B minus R2. So that is, you take A times B, which is the set of pairs, the set of all possible pairs from A and B, and you take out the elements of R2 from there. So that gives you, well, A times B is really just 1, 1, 1, 2 up to, of course, 3, 4. Right, there are 12 pairs of them, minus, of course, 1, 1, 1, 2, 1, 3, and 1, 4. Now this gives you, well, that means you have 2, 1, 2, 2, 2, 3, 2, 4, and and of course, well, 3,1, 3,2, 3,3, and 3,4. So that's a complement of R2. So you see this example. Now let's try an exercise. So now you're given a relation R1, which is the set of pairs of real numbers x and y, such that x is less than or equal to y, and the relation R2 defined over reals, where a pair x comma y is in R2 if and only if x is greater than or equal to y. Now let's do this exercise, and we shall discuss the solution in the next video.